Hey everybody, it is week 9. I'm tired. You're probably tired too. So we're gonna get started. This week we are continuing our discussion of double integrals, and we're going to look at double integrals where the region in which we're integrating is not a rectangle. And then we're going to develop the notion of polar coordinates to deal with non-rectangular regions that are difficult to interpret in rectangular coordinates. Last week, we were always integrating over rectangular regions. We knew that our x was varying from one number to another number, while our y was varying from one number to another number. In total, we ended up with that rectangular region for which we were taking the integral. But what if we want to calculate double integrals where the region for which we're integrating is non-rectangular? An example there would be if I have a curve that looks like this. Oh, not like that. A curve that looks like this, and a curve that looks like that. If I look at the region in between these two curves, call this a region R, how am I going to represent a double integral over this region? In order to deal with that, we are going to again use the notion of an iterated integral and then define limits of integration appropriately. Let's try to figure this out with a slightly easier example. Suppose that R is the region bounded by y equal to x squared and y equal to 1. This can be represented by drawing our curve y equal to x squared, which looks something like this. So here's my y equals x squared. And I could also have my curve y equal to 1 somewhere around here. So here's my y equal to 1. The region R for which I'm integrating over is going to be the region between the pink and the blue. So this area that I'm shading here in yellow is my region R. So here we've got our region R. Now, we want to try to set up an iterated integral. And to help us out here, what we want is we're looking for a volume, which is going to be equal to the integral over our region R of f of xy and then dA. We know that with iterated integrals, we can either set this integral up as dx dy or dy dx. But here in this problem, we're specifying to set it up in dy dx. We can do the other way as well. So we'll have our f of x comma y, and we want to set it up dy dx, looking at the change in y and then looking at the change in x. So we want to figure out, well, how is our y changing? If we look at the region here, so at this particular value of x, we can see that our y value is changing from the point here, which is x squared, all the way up to the point y equal to 1. In total, our y is changing from x squared to y equal to 1. To figure out the change in x, we need to see where our x is varying. And here, if we pull down the points of intersection, we can see that this point here, after a little bit of algebra, is going to be -1. And then here, the point of intersection is also going to be +1. And so while our y is varying from x squared until 1, our x values are varying from -1 to 1. I'm going to take that change in my y for all kinds of values from -1 to 1. Which gives us this as an integral, an iterated integral representing the volume. If instead we want to represent this as an iterated integral in dx dy, what we're trying to figure out are the limits of integration for f of xy, where I take dx dy. We need our change in x and then our change in y. So for a change in x, we can see that if we choose a value of y here, our x's are going to vary from one value to another value. So here I choose a particular value of y, and I see that my x is going to be varying from, in this case, my value is going to be negative root y all the way to positive root y. So in total, we would end up getting that this is going to vary from negative root y to positive root y. And we're going to do this kind of movement for all values of y that are varying from 0 until 1. I'm going to take that orange line, I'll take this orange line, etc., doing that for values of y between 0 and 1. Let's go ahead and calculate this iterated integral. And in this case, I'm going to assign f of x comma y to equal x times y so that we can evaluate this integral. Then I would get that v is going to be equal to, let's go ahead and do the dy dx1. So we have -1 to 1, and then x squared to 1 of xy dy dx. We are integrating with respect to y first, and so here we're going to have that integral on the outside, -1 to 1, and then the antiderivative of xy with respect to y is going to be xy squared divided by 2, and we're going to evaluate this from x squared to 1. And we've got that dx there on the outside. Then, evaluating these limits of integration, we have -1 to 1, our outside integral, and we'll end up with, remember that this is our y equal to 1 and y equal to x squared. So that's going to give us, we'll have just x over 2, and then minus, we'll end up with x times x squared squared, which will give me an x to the power of 5 divided by 2, all dx. Then we can finish this up as we would solve a general single integral. So we have that this will give me 1 over 4 x squared minus 1 over 12 x to the 6 from -1 to 1. And evaluating this, we will get a total value of 0 for the volume underneath of this curve on the region given here. You probably gathered from that previous example that setting up iterated integrals is the hardest part of dealing with double integrals. So we're going to spend a little bit more time seeing some examples of setting up these limits of integration on double integrals. Here we have an example where we have a triangular region that's defined by looking at the area underneath of the curve y equal to 1 minus x and above the x-axis. So the region that I'm looking at is this region here, which we call our region R. So here is the region R that we are going to be working with. Okay, so we want to set up two iterated integrals. We have our volume, which we know is the iterated integral, or the double integral, over R of f of x comma y dA. And we're going to set up two integrals. The first one that we're going to set up is going to be f of x comma y dy by dx. And the second one that we're going to set up is going to be the integral of f of x comma y dx dy. So to start off with the first example, so our dy by dx, we want to pick a value and see how y is changing and for what values of x we're doing that. I think it's easier to go from the outside in. So you should always have that the outside integral has constants. So here, my x. For what values of x am I taking heights? I'm going to be doing that from x equals 1 all the way to x equals 0, all the way to x equal to 1. That is my point of intersection here. So I've got 1 here, and I've got 1 there. So I know that I should be taking this from 0 all the way, so for my x equals 0, all the way to my x equals 1. And I'm taking those changes in y for all of those values of x. So I'm doing that for this value x, this value of x, this value of x, all of them from 0 to 1. And so I then, at that value of x, I need to think about, okay, well, how is my y changing now? And that's where these arrows come in. And we can see that our y values are always starting at 0, and I'm going to take those y values all the way up to y equal to 1 minus x. So I'll end up with y equals 0 to y equal to 1 minus x. We can simplify this by just writing the integral from 0 to 1 minus x and the integral from 0 to 1. And we'll do that on the next iterated integral. For the second iterated integral, again, going outside in is the best way to go. So here we're dealing with dx dy. We want to think about how is our y changing. We expect and need these integral limits to be constants. We are going to be taking values of y between y equals 0 until y equal to 1. So once again, we're going to get 0 to 1 as our limits of integration, but again, note that these are values of y rather than values of x. On the same idea for figuring out change in x, I choose a specific value of y, and then we can think about what the change in our x is. So I end up with that arrow and line, this line, and so forth for all of these different values of y. And here, again, we can see, well, I'm always going from x equals 0, and then I'm getting to this point here. And in order to get to this point, well, it's on the line, and we can use the fact that, well, the curve is y equal to 1 minus x, but this is the same as saying that x is equal to 1 minus y after we move things around. And so my x is going from 0 all the way to 1 minus y, giving me the limits of integration of 0 to 1 minus y. This example is very similar, but the setup is going to be a lot more challenging. Here, we're setting things up, starting off with our curve. We have y equal to x squared, which I can draw as follows. So here's my y equal to x squared. And I also have my line given by 2 minus x, which we can draw here. So here's y equal to 2 minus x. According to the information here, I'm looking for y values bigger than x squared. So I'm looking for values above the parabola, but I'm also looking for y values underneath of the line. So in total, my region, R, is this region defined here. And this is the region that we're going to want to set up our iterated integral. To do that, again, we're looking at the volume is going to be the integral over the region R of f of x dA, f of x y dA. And again, we're going to get two integrals out of this. The first one is going to be in terms of dy by dx. And the second one is going to be in terms of dx dy. For the first case, again, moving outside in, we need to think about what our values of x can be. So again, the integral limits here should be numbers. Our x values are going to be changing based on the points of intersection here. So here I could pull this point down and with a little bit of algebra show that that is -2. And same thing here, pulling this point down, I'm going to get a point of intersection of +1. So it means that my x values are going to be changing between -2 and 1. And I'm going to be taking those slices for different values of x. I want to think about, for the values of x between -2 and 1, how is my y changing? Again, I'm going to have these kinds of bars that are going to represent how my y is varying. And here we can see that the y is varying from x squared all the way up to the top curve of 2 minus x. So that's going to give me limits of integration being x squared all the way to 2 minus x. Setting up the dy dx integral wasn't too bad, but setting up the dx dy iterated integral is going to be kind of nasty. We can see that because if we start drawing out those horizontal bars, so if I draw a horizontal bar here, a horizontal bar here, a horizontal bar here, and so forth, again, I can see how my y is varying. But notice something interesting. If we look at the outside variables, so y, if I choose these values of y, something funky happens at the point y equal to 1. Because that's the point where instead of going from blue to blue, I start going from blue to green. So we can break up the iterated integral as f of x comma y dx dy plus, again, another iterated integral of f of x comma y dx dy, where we see, okay, something is happening from 0 up until this value of 1. So I'll have from 0 to 1. And then something different is happening from 1 up until I take my last point here, right, my last little rectangle up here, which is going to be 4, after, again, a little bit of algebra to realize that that is going to be 4. So I'll end up getting 1 to 4 here. Now the question is, what are those limits of integration going to be? And again, we want these to be expressions in terms of x. So we need to do a little bit of shifting. We can rewrite y equals to x squared. We know is going to be that our x is equal to plus or minus root y. And then we also have here that our y equal to 2 minus x can be rewritten as x equal to 2 minus y. So on the interval from 0 to 1, I see that I'm going from negative root y to positive root y. So there I can switch that up, negative root y to positive root y. Meanwhile, when I look at 1 all the way up to 4, again, I'm going from the blue part on the negative side to the green part over here. And so that means that I'm going to be moving and having my x values vary from, I'm changing my color to match here, negative root y to my green curve, which is going to be 2 minus y. Setting up the iterated integrals can be challenging. Another challenge is that sometimes the order that your integral is presented in cannot be evaluated. If you took 112 with me, you'll remember we did quite a bit of work on this function and this kind of integral, except the negative, that's the error function, which you may see in your probability and physics classes. But here we can note that, well, if I try to evaluate this integral, I don't have any techniques of integration that'll work here. So the issue is that this integral, so we can't evaluate it in this order. And so the idea is that we want to change the order of integration so that we can evaluate the iterated integral. To do that, we're going to want to try to figure out what the region is based on the limits of integration, which is pretty tricky. So here we can draw out our xy coordinate axes. So here's my y and here's my x. Remember that the limits of integration here, we know that this is from x equals 3y to x equals 3, and y equals 0 to y equals 1. We can draw out some information here because we've got x equal to 3y, and this is the same as having y equal to x over 3. And this is a graph that we can draw. So we know that this function looks something like this. And that's not as good as I wanted it to be because I want it to go right through the origin, and it's not doing that. So let's try there. Not great, but we're going to go through it. So there's our line. And then the next thing that we have is x equal to 3. So x equal to 3 gives me this as a line, and this will be nice and straight. There we go. So my x equal to 3, and then my line y equal to x over 3. So we're varying between y equals 0 and y equals 1. That's going to be that point of intersection. So here I end up getting 1. So the region, based on this information, is going to be this triangular region here. And now we want to translate this so that instead of the integral being in dx dy, it's in dy dx. So this is going to be equal to, we're going to switch it up. So instead of having e to the x squared dx dy, we'll have dy dx. And we can draw out our little changes here. So my x's are going to be varying from 0 until 3. So that means that my outer limits of integration are going to be 0 to 3. My y values, again here, drawing our little parts to help us figure out that change in y, we can see are varying from y equals 0 to y equals x over 3. So we switch from y equals 0 to y equal to x over 3. And now this is a double integral that we can evaluate. We end up getting here, so in the first bit, we get 0 to 3. The antiderivative of a constant with respect to y will be that constant times y. So here we'll get y, e to the x squared, from 0 to x over 3 dx. I'm going to ask you to pick this one up and finish it. By the time you pause the video and come back, I'll have it all done. In the end, you should have gotten 1 over 6 times e to the 9 minus 1 as the value of this integral. You needed to use a u substitution once you got to this point, and then making this single integral into a nice integral with just e to the u makes it straightforward to evaluate. In this example, we actually have to figure out what our region is based on the information that we're given here. To start things off, we've got 2 paraboloids, and I'm going to go ahead and plot these in my 3D coordinate system. So here I have my first curve, and I'm going to label it in green, is going to be z equal to 2 minus x squared minus y squared. That's going to look something like this. And then putting a 3-dimensional look to that. And then for our other surface, so that's going to be in blue here, this is a paraboloid that's going to be facing up and have a vertex at the origin, so it's going to look something like this. We end up with a kind of egg shape for what we are trying to find, the volume of. Okay, so here we've got this shape, and now we need to figure out what our region is. So let's think about that for a second. the region that I'm integrating over is always going to be in the XY plane. They're going to be points for which I'm going to generate some kind of a tower. So I could choose this point here and get a really small tower, another tower, towers all through this volume. And so what we need to figure out is, okay, well, what happens if I project these points down? Because it seems like I'm not going to take towers for points outside of this kind of widest area. And so we need to figure out that the region of integration is going to be determined here by where these surfaces intersect. So is determined by where these surfaces intersect. And we can do that algebraically. So here we want to know when these two curves are going to be equal. So that means we want to know when 2x squared minus y squared is equal to x squared plus y squared. A little bit of algebra brings us to 2 equal to 2x squared plus 2y squared, which means that 1 is equal to x squared plus y squared. Our intersection is going to be given by the unit circle centered at 0, 0. So here, my unit circle is here, and I've got 1, -1, 1, and so forth. So here with my y and my x. I need to integrate for all of the values and points x and y that are inside of this region. Because if I project this down onto the xy plane, what I am getting is going to be the circle that's seen over there. So trying to draw this out, the region here is what we are integrating over. So now if we want to set up our volume integral, we're saying the volume is going to be some iterated integral. Here we can think about what our towers are. So here we end up with our towers are always going to be the top tower minus this bottom tower. So in total, the top function minus the bottom function, which gives me 2 minus x squared minus y squared minus my bottom function, x squared plus y squared. I should have labeled these more carefully. So remember, our bottom curve is z equal to x squared plus y squared, and our green curve is y equal to 2 minus x squared minus y squared. Now we need to have those limits of integration. Personally, I always like trying the integral of dy by dx first. So here we know that we want to take our limits from x equals -1 to x equal to 1. So I'm going to end up with -1 to 1 for my values of x, where I'm taking those towers. So then, same thing, we want to look at the changes in y for those different values of x. And we got to be a little careful again, because here we have the bottom half of the circle and the upper half of the circle. The upper half of the circle is given by y equal to the square root of 1 minus x squared, whereas the bottom half of the circle is given by the negative of that square root. So we actually have two functions of x that we need to be aware of in setting up our limits of integration. So there we see that, again, the y value goes from that negative square root up until that positive square root. And so we can replace these limits of integration into our iterated integral to have an expression for this volume. You can probably imagine that if we evaluated this integral, it's going to be pretty nasty. Not too bad, thankfully, because these y's are squared. But then once I take the derivative with respect to y, those are going to become y cubes, and then I have to input this. So I'm going to have the square root of 1 minus x squared to the power of 3, which would require us to use trigonometric substitution a number of times. We don't want to do that. And so we're going to end up with a new technique for translating integrals where regions are circular into slightly less complicated integrals, and that's coming up on the next slide. So the previous example was bad enough. Let's go ahead and see another example where even just finding limits of integration is going to be really challenging. So suppose that we have a region between two circles. So here, the region that I am looking at is going to be this region here. Now, imagine that you wanted to try to set up limits of integration in our standard Cartesian rectangular coordinate system, but for these circles. So here I've got my outside circle is going to be x squared plus y squared equal to 9. Whereas my inside circle is going to be x squared plus y squared plus 1, or equal to 1, sorry. The issue here is that trying to set this up, so trying limits in the rectangular system is going to be really awful. We don't want to even try to do that. It's just hard. If you try, kudos on you, but it's just more work than you need to do. And as such, we're going to come up with a method to switch this region from rectangular coordinates x comma y to what are known as polar coordinates. Some of you saw polar coordinates in Math 111, but I know that a lot of people didn't. So I'm going to spend a little bit of time here going through polar coordinates to get us used to working in this system. The idea in polar coordinates is that if I choose a point P equal to x comma y, yes, this point P is determined by the value x and the value y on the x and y axes, respectively. But we have a different way to determine where this point is in space, and we do that by looking at the line that is connecting P to the origin. This line can be uniquely determined by, first of all, the length of the line. We'll call that length r, and by the angle theta for which we take that line and length away from the x-axis. So instead, what we end up getting is that our value of x is going to be equal to r cosine of theta. Our y is going to be equal to r sine of theta. We also know that x squared plus y squared is going to be equal to r squared, since this point is going to be on the circle of radius r. And we also know that the tangent of theta is going to be equal to y over x. As a side note, we are always going to have that our r, in this case, is going to be bigger than or equal to 0 because it is representing a radius. We can then take this idea of points, instead of being x comma y, to being these forms to help us rewrite the region on the previous slide in terms of our polar coordinates. So in that case, what we end up having is that the region R is going to be equal to points of the form r comma theta, such that, well, our radius values, if we go back here, are always going to be ranging between 1 and 3. R will be between 1 and 3. So we can replace that in here. So we get that 1 is less than or equal to r, is less than or equal to 3. And then we also have that our angle is going to be shifting from 0 all the way to 2 pi. We're taking all values of theta, from 0 until 2 pi, which can then translate to 0 less than or equal to theta less than or equal to pi, 2 pi. Now notice what this region is in the polar coordinate system of r and theta. We have that our r is between 1 and 3, and our theta is between 0 and 2 pi. I have now shifted from a region that previously was what we call an annulus to now a rectangular region that I can much more easily set up an iterated integral for. Let's look through a few more examples. I'll work through the first one, and then I'll ask you to set up the second one. For the first example, we're wanting to find the region bounded by this curve and the y-axis. This is the positive side of a semicircle, and we can graph it like so. So it's going to be, actually, I will just draw out a full circle and then erase. So there is a circle. We can erase the negative side. And so the region that we're looking for is going to be this region here. And so now we want to try to set up our region R to be equal to, again, it's going to be in terms of R and theta. My radius is always going to be between 0 and this value here, which we know is going to be equal to 2. So here we know that this is going to be -2. I get a +2. Here again, 2. So my 0 is less than or equal to r is less than or equal to 2. For theta, we're taking theta values from -pi/2 all the way to pi/2. So we end up getting -pi/2 less than or equal to theta less than or equal to pi/2. Once again, a rectangular region in polar rather than this semicircular region in x and y. Give the second example a try. I'll have it all worked out by the time you come back so that we can save a little bit of time on this video. You should have gotten this as your expression for the region defined here in 2. The key here to note is that r is always going to be positive. So here we've got that +3 radius to a +4 radius, taking our radii here, while our theta value is going to range from pi all the way to 2 pi. In both of these instances, we go from a circular region in some way in the Cartesian plane to a nice rectangular region in r and theta. Integrating iterated integrals over a rectangle is going to be way easier than integrating over some kind of a circular region. Before we move on back to integrals, I want to spend one more difficult example working through polar coordinates. In this example, we're looking at a region between two circles, and I've labeled these in green and blue. So here we've got x² + y² = 1 in blue, and we have x - 1² + y² = 1 in green. We want to first find the region that we're looking for. Apparently it's outside of the green circle, but inside of the blue circle in the first quadrant. So the region that we're actually looking for is this funky region here that I'm shading in yellow. Before we try to figure out what that region is, we want to try to figure out the polar coordinates of both of these circles. We can do that by using what we know about the polar coordinate system. I have x² + y² = 1, but I know that x² is going to be r cos theta, so that will give me r² cos² theta, plus, similarly, I get r² sin² theta, since my y should be equal to r sin theta. Simplifying a little bit, we get r² as cos² theta plus sin² theta = 1, But we know that this expression is always equal to 1. So this gives me that my r squared is equal to 1, which implies that r should be equal to 1 because we know that r is always going to be bigger than or equal to 0. For circle number 2, we have a similar strategy. We're going to take the x minus 1 squared plus y squared equal to 1 and switch it into r and theta. Give this one a try. You should have gotten that r is equal to 2 cos of theta. You could do this by immediately substituting in r cos theta and r sine theta for x and y respectively, or you could go ahead and do the algebra at the very beginning. We know that this x squared plus y squared should be equal to r squared, and then I end up getting that 2x giving me 2r cos theta. Dividing both sides by r, we end up with r equal to 2 cos theta as the polar equation for the green circle. From here, we want to describe this region in polar coordinates. And in order to do that, we need to figure out the point of intersection, because essentially I'm looking at the little slices in this highlighted region. And we're going to be doing that for certain values of theta. So the question here is, where do they intersect? And this can be figured out algebraically. So in this case, we want to know when 1, my r equals 1, equals r equal to 2 cos of theta. This is going to happen when my cos of theta is equal to 1/2, which is when my theta is going to be equal to pi over 3. So pi over 3 is going to be where I have that initial intersection here of these two circles. So there is my angle of pi over 3 to give me that point of intersection. Now we need to move on and figure out what this region is. So in this case, we are working with a region D, which we know is going to be equal to r comma theta, such that, well, we can figure out, I think it's a little easier to figure out theta first. So my theta is ranging between pi over 3 and pi over 2. So we've got theta is bigger than pi over 3, but smaller than pi over 2. Why? Because I'm taking all of these theta values from pi over 3 to pi over 2. Our r values need to be given a bit more thought. So we're trying to figure out where our r values lie. And again, here we need to go ahead and look at, I'm going to switch to pink to see, and I'm actually going to zoom in so you guys can see my screen. Here, we're looking at the radius from here to here for this different angle from here to here, this different angle from here to here, and so forth. These are all of the changes in radius that we need to figure out. We can see that the small radius is always going to be in terms of our green circle, which was given by the equation 2 cos theta. So we see that we should have that we get 2 cos theta here. And our outer r value is always going to be on the blue circle. So that is going to be less than or equal to 1. So that gives me my region D. Now that we have an understanding of polar coordinates, I want to shift into discussing how we can use polar coordinates in double integrals. Remember that the motivation for switching to polar coordinates was that sometimes we could have a circular region that would end up with limits of integration that resulted in a really nasty integral to evaluate. As such, we've developed these polar coordinates which translate circular regions into rectangular ones. The gut instinct might be to say, well, okay, I'm just going to change my x's to r cos thetas, my y's to r sine thetas, and change dA to dr d theta. Unfortunately, dA is not equal to dr d theta, and we can show this geometrically. Suppose that we have a angle, a very small angle, which I'm going to call my d theta. So this is a tiny change in an angle of d theta. And I could have that my bottom here, the length at the bottom of this, I could call this length r. To this r, I could think of a tiny increment of r, which I'm going to call my dr. So here's a tiny little part, which I will call dr. And from here, I can think about the area that I would generate if I moved dr by this angle of d theta. So what would happen here is I would end up with a kind of shape that looks like this. And I would end up with a tiny area. I have my tiny dr, and I also have this tiny d theta. This ends up being, this shaded green area, is what I have as dA. From here, we need to do a little bit more. We can recognize that in this case, I have that the length of this side is going to be whatever my r is times my angle. Essentially, this is going with circumferences of circles and parts of circles. You can think of the circumference of a circle is 2 pi r. It's taking that r and then rotating it by 2 pi. Similarly, if the angle is pi, I'm taking my radius and then I'm multiplying it by pi. In this case, the length here ends up being r times d theta. And in total, what we end up getting here is that our dA on an infinitesimal level. So that's the important thing here, is that everything is very, 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 very small. So we've got an infinitesimal level. What we end up having is that our dA is going to be equal to our length, which is r d theta times dr. So we end up getting that it's equal to r times dr times d theta. And as such, we have that if we ever want to switch a integral from Cartesian coordinates to polar coordinates, we make the replacement of our x and y as r cos theta and r sine theta. But we have to remember that dA is going to become r dr d theta. Be aware that that r is really important and you can't forget it. Now we're ready to go ahead and tackle an integral and switch it into polar coordinates. Here we have a double integral in x and y, and we're wanting to find the integral over the region x squared plus y squared less than or equal to 1. Again, we could go ahead and try to do this in rectangular coordinates, but it's going to end up with a nasty integral that's going to be quite difficult to evaluate. So we can switch this into polar coordinates first by thinking about what this region is in polar coordinates. We can do that by going ahead and drawing out our xy coordinate axes, and then getting our region here, which is going to be the unit circle with a radius of 1. So here is going to be my region R, for which I want to find the integral. So here is my disk R. Translating this into polar coordinates, we can see that our region R is going to be equal to points r comma theta such that 0 is less than r is less than or equal to 1. We have all of the radii from 0 to 1. And our thetas are going to range from 0 to 2 pi. This allows me to now go from coordinates that are in x and y to now translating into coordinates of r and theta. So here I have my r, I have my theta, and we're going to have that r is going to range, our radius will range from 0 to 1, while our theta will range from 0 to 2 pi. So we're going to be integrating over the rectangular region denoted here in r and theta, which is certainly going to be easier to set up an integral for than when we have this non-rectangular circular region. Now we're at a point where we can evaluate this into polar coordinates by making all of our substitutions. We switch our original integral, changing our limits of integration, but first I think it's helpful to write out the inside. We're going to change our x's to r cos theta, so we'll get 3r cos of theta. Our y's are going to change to r sine of theta, and I've just got that single y there, and then I'm going to have plus a 2. Now, careful here, all of this is going to get multiplied by dA, but we know that dA is going to be r dr d theta. Can't forget that extra r there in our switch to polar coordinates. We're integrating with respect to r first. We can see that r is changing from 0 to 1. So I'll have those 0 to 1 limits. And similarly for d theta, I'll have 0 to 2 pi. Now we're at a point where we need to do a little bit of algebra, distributing this r through the parentheses. So I end up with the integral 0 to 2 pi, another integral from 0 to 1 of 3r squared cos theta plus r squared sine theta plus 2r dr d theta. Now we need to evaluate this integral from the inside out. So focusing on our dr integral first, treating theta as a constant, we're going to have that this is the integral from 0 to 2 pi on the outside. So that's our d theta integral. Integrating with respect to r, we have that the antiderivative of this term is going to be 3r cubed divided by 3. So in total, I'll just end up with an r cubed times our constant cos of theta. We'll end up with an r cubed over 3 times sine of theta, since it's a constant. And lastly, we'll end up with the antiderivative of 2r will be 2r squared divided by 2, or just an r squared, for which I'm evaluating this from 0 to 1, and I've got my d theta there on the outside. So now I've got this inside bit here in my pink brackets that I need to evaluate. Going ahead and doing this, we end up with the integral from 0 to 2 pi, and evaluating from 0 to 1, we'll end up with just cosine of theta plus 1 over 3 sine of theta plus a single 1 d theta. And now we're down to a single integral that we can evaluate directly. Here, the antiderivative of cosine is going to be sine of theta. We'll get a minus 1 over 3 cosine of theta, and the antiderivative of 1 with respect to theta is going to be plus a theta, which we're evaluating from 0 to 2 pi. Evaluating this from 0 to 2 pi will give us a final result of 2 pi as the volume underneath of this surface on the disk given here. It's been a while since I've given you a chance to give things a try. Here we have a different function that we're wanting to evaluate the volume of under a region here defined by the area between the circles given by these two equations. In total, what we want to find is the volume, the double integral over the region R of this f of xy, which is e to the negative x squared minus y squared dA. In this case, what you're going to need to do is you need to find out what the region is, switch it into polar coordinates, and then set up an appropriate integral in polar coordinates. Give this one a try, and I'll have it all worked out by the time you come back. In the end, you should have gotten this as your final answer for the volume of this integral. Here we need to do a little bit of algebra in order to set up our integral, again remembering our r dr d theta once we make our replacements for x and y as r cos theta and r sine theta respectively. Here we have our region, which we can throw into polar coordinates, seeing that our r and our theta are going to be alternating and changing for r between 1 and 2, and our theta is going to be between 0 and 2 pi. From here, then, we just have to do a bit of algebra, noting here that we can end up taking out a negative r squared as a common factor, which would just leave us with cos squared plus sine squared, which we know is 1. Thus, the inside of the integral changes just to e to the negative r squared times r dr d theta. So here, then, we can go through and do a u substitution. So we can substitute in our u as negative r squared so that du is negative 2r dr. And changing our limits of integration to be in terms of u, we end up with this integral. We can evaluate this directly. The antiderivative is just the function itself from negative 1 to 4, which we evaluate, and it gives us this as the inside. Then we have the integral from 0 to 2 pi of this expression d theta. Both of these are constants, so the antiderivative is just going to be this times theta and this times theta. We evaluate this from 0 to 2 pi, and we should get pi times e to the negative 1 minus e to the negative 4 as our final answer. In both of those examples, the really nice thing was that when we went from our rectangular coordinate region to polar coordinates, we ended up with a rectangular region in r and theta to set up our integral. So with respect to the previous example, note that what we started with was I had that outer circle. So here, this will take a little bit of time for me to set up. And then I had my inner circle, which I could represent here. So slightly off in terms of scale, but it's okay. So here I have that region between these two circles is given by a rectangular region. I had that my r was ranging between 1 and 2, while my theta was ranging between 0 and 2 pi. So here we end up getting that, okay, I've got 1 to 2 because I have my x squared plus y squared equal to 4, and I have that x squared plus y squared equals 1. So this region, when I translate into the r and theta coordinates, being really careful of these variables, we're switching, again, 0 to 2 pi for my theta. So the region becomes something a little bit nicer than what we had before. So I end up with, and just to adjust here and make my life a little bit easier, we end up with that region translating into polar coordinates in this nice rectangular region. The question that we want to ask now is, well, what if when I make this transition from my Cartesian coordinate system to my polar coordinate system, what happens if my region is not rectangular? In this example, we want to find the area inside of the circle given by this equation and outside of the circle given by this equation. We worked with these exact same circles a few slides ago, where we wanted to try to find a different region in polar coordinates, that region being this part here. Rather, now what we want to try to figure out is what is the area inside of the orange but outside of the green. So that is going to be this region here that I can shade around in yellow. So in this case, again, we're going to want to try to figure out what this is in terms of polar coordinates to help us figure out how we can set up an integral. We spent time working with these circles and finding out what the polar equations of these circles are. If you forget how to do that, I recommend going back to earlier in the video when we did that. But here, I'll just go ahead and remind you that the orange circle here was given by the equation r equal to 2 cos of theta, while the green circle was equal to r equal to 1 in polar coordinates. Here, we're trying to find the area, so we need to do something a little bit different in terms of setup. We're really trying to find the area of the region R, where that R is that highlighted yellow region. And we're going to do this in terms of a double integral. But again, we're not finding any kind of volume underneath of a curve. Really, all I want is just when my z coordinate essentially is 1. So we can just think about this as being the double integral with just dA. So I'm not having any kind of change in my height of the function over my region R. And so we want to set this up as some kind of an integral in terms of polar coordinates, where my dA is going to be r dr d theta. We need to figure out how our radius is changing and also how our theta is changing. And here we can see that, well, for my various values of theta, well, what are my values of theta? I'm taking values of theta from whatever this is all the way until theta being equal to, if you remember earlier in the slides, we found out that this point of intersection was happening when our theta was equal to pi over 3. So remember that this was happening at pi over 3. This is also going to be symmetric across the x-axis, so we would also know that this angle should be equal to negative pi over 3. In total, we're going to be integrating from negative pi over 3 to pi over 3 for our values of theta. Now, when we want to think about our r values, our radius is going to always be on some little part here. So switching to different color. So we're looking for these radii. And here we can see that we're always starting at 1, and then our outside is always going to be 2 cos theta. So I go from 1 to 2 cos theta, 1 to 2 cos theta, and so forth for all of those different values of theta. That means I can switch these limits of integration to go from 1 to 2 cos of theta. And now we're at a point where we can evaluate this double integral. To evaluate, we need to integrate with respect to r first. In doing that, we're going to get the integral on the outside, negative pi over 3 to pi over 3. And in the inside, integrating with respect to r, we're going to get r squared over 2, evaluated from 1 to 2 cosine of theta, d theta. And then we're going to get that this is the integral from negative pi over 3 to pi over 3 of, we'll substitute in our 2 cos theta. So in total, that's going to leave me with 2 cos squared of theta. My 4 cancels out with the 2 in the denominator. And then we're going to be subtracting a 1/2 and then d theta. See if you can finish up this integral from here. You'll need to maybe return back to your Calc 2 notes where you have to do a kind of nice substitution using a trig identity to get this 2 cos squared theta to be a little bit easier to evaluate. Pause the video, and by the time you come back, I'll have it worked out. In the end, you should have gotten this as an expression. We could have gone ahead and simplified it further, but that would just take a little bit too much time that I don't want to spend doing on this video. So the big key here is to make the trigonometric identity substitution that cos squared of theta is going to be equal to the double angle formula 1 plus cos of 2 theta divided by 2. Once we make that substitution, we can do a little bit of algebra, seeing that we'll end up with just a 1 plus cos of 2 theta minus a 1/2. Then we can integrate with respect to theta, and we'll end up with just theta plus 1/2 sine of 2 theta. You could go ahead and do a u substitution there, and then we'll have a minus 1/2 theta. And we're evaluating this from negative pi over 3 to pi over 3. Finally, we take the antiderivatives, or we've taken the antiderivatives, so now we just need to evaluate. I did a little bit of extra algebra, noticing that theta minus 1/2 theta will leave me with a theta over 2. And then evaluating from negative pi over 3 to pi over 3 gives me this as my expression for the area highlighted in yellow here.